All right, this is AP, AB, and BC Calculus. We're doing Unit 6, Section 2, which is approximating areas with Riemann sums. So let's go ahead and get started. So the area under a curve can be approximated by several methods. In this video, we're specifically going to focus on methods involving rectangles. We're going to walk through 5 of them. Left Riemann approximation method, that's LRAM. Right Riemann approximation method, that's RRAM. Upper sum, lower sum, and midpoint Riemann approximation, which is MRAM. So in calculus, you'll be asked for this method expressly. So for a method expressly, rather. So the problem will say using blank, like just to show you what I mean by this, they'll say something akin to using LRAM with 4 boxes, right? Estimate the area from x is 1 to, I don't know, 9, right? They're going to clearly give you that information. So you're not going to have to ask yourself, oh, should I use LRAM or RRAM? That's not going to be the case. It'll be very clear that they ask you for a method. The only difference between these 5 methods is which y value you're going to use for the height of each box in each interval. And then at the end of this video, we're going to learn to use one non-rectangular method for area approximation, which is called the trapezoidal rule, and we'll discuss another one that you're not going to see on your AP, but I just want to throw it out there, and that'll be Simpsons rule. So let's go ahead and get started. So if you have boxes of equal width, which is frequently going to be the way that these questions are worded, let's say you have n boxes of equal width, and you're approximating the area from x is a to x is b. So what we're saying here is you have some curve from x is a to x is b. So your interval is from a to b. You're going to divide it equally by n boxes. Well, that means that the width of one box is going to be b minus a, this entire width, divided by n boxes, okay? So the width, right, which we'll sometimes see as delta x, is b minus a over n, okay? So the height of each box. So each box has a y value as an endpoint, right, on the left side, and a y value as an endpoint on the right side of the box. So just to show you what I mean by that, let's see if I can draw you a tiny little version of a graph. So let's say we have a curve that looks like this, and let's just say we have 2 boxes. So let's say these are my 2 boxes, right? So there's a y value on either side of this window, right? And then here's my second box, and there's a y value, a left and a right y value, and then this is the left and the right y value, right? So which of these 2 y values I use to create the box's height is going to depend on which of the methods I was asked to use. So for LRAM, I would use the left side of this box and create a rectangle. Now it turns out that the box I drew, they're kind of the same, so let's just put the dot there instead. So left box and then left box, right? If I were using RRAM, I would take of these 2 endpoints and I'd use the right endpoint for this window and the right endpoint for this window, right? Upper sum means pick the higher of the 2 y values, right? So in each interval, one of the 2 values is higher, pick that one. Lower sum means pick the lower of those 2 endpoint values because it's lower sum. And MRAM means you find the middle x coordinate and then go up to the top of the curve, find the curve, and that's the height you use, okay? So to find the area, each one of these is a rectangle. So to find the area of a rectangle, we do base times height or width times height, whichever way you want to think about it. And then you add up all those n rectangles to get an approximation to the area under the curve. So we're going to do a bunch of problems like this with different approximation methods. So example 1. Use the methods indicated to approximate the area of the curve, which I conveniently graphed for you and labeled the points because I decided to be nice, from -1. So we're starting at -1, which is right here, right? And we're going to go up until 3, which is right here. And I apologize in advance for my inability to draw straight lines when doing this, but you get the gist. So we're going to approximate the area under this curve using 4 boxes of equal width. So the first thing I have to notice is that the width of each box, right, is going to be b minus a all over the number of boxes, which in this case means my boxes are a width 1. And that kind of fits, right, because what's happening here is we have one box here, right, and then another box here, and another box here, and then here's my 4th box. So 1, 2, 3, 4 boxes, and depends on the height. So let's start with LRAM, okay? LRAM means that each one of these boxes, I'm going to take the left of the 2 y values and draw a box across. So left y value, draw a box. 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 So using the left y values, I get that the area for LRAM, right, is approximately this first box, right, is a width of 1 times 3 units high. The second box was a width of 1 times 2 units high. The third box was a width of 1 times 3 units high. And the last box was a width of 1 times 6 units high. Now, another way to write this, because they all have the same width, is you could actually factor the width out and notice that you're just adding the y values, right? And what's interesting about this is essentially I'm adding all of the y values that are not the rightmost point. The only y value I didn't use was the very rightmost y value. So that's kind of useful, and we'll come back to it later. So I seem to get this as a 1 times what looks to be a 14. So I get that the area is 14 if I do LRAM. So now I'm going to erase. Okay, and in a different color. So let's go ahead and pick red for RRAM. Okay, so we'll do red for RRAM. So now I'm using the right endpoint. So again, this first box, right, I'm going to take the right endpoint and draw a box. Second one, I'm going to take the right endpoint and draw a box. Right endpoint and draw a box. And right endpoint and draw a box, right? So it's not the prettiest graph you've ever seen, but you can see that these are all boxes with the right endpoint as the y value, okay? So what ends up happening is I get that this is 1 times the y value from the first interval, which is 2, plus a width of 1 times the 3, which is the height of the second box, width of 1 times the sixth, and lastly, a width of 1 times the 11, right? Again, if you wanted, you could also have noticed that you can factor out that width. That works anytime the width is constant, which it is in this case, right? And if I add these together, I seem to get that it's approximately 22. Now you'll notice that that is definitely more area than the actual quantity, because you can see that these areas are higher than, there's a lot of extra, right? And there's only a little bit of underestimation. So it's a lot more than the actual area under the curve, right? So there we go. So that's RRAM, right? And then the last one, we're going to do an upper sum. So let's do that one in green, okay? So upper sum means that each interval has two y values, pick the higher one. So in this first interval, right, from -1 to 0, this is clearly the higher y value, so I pick that one and draw the box at 3. In the second interval, my two y values are also, again, 2 and 3, just like we saw, but I pick the higher one, so it's 3 because it's an upper sum. In the next interval, the two y values are a 3 and a 6. 6 is obviously the higher one, so I draw the box at 6. And then my last interval has y values of 6 and 11. Well, 11 is the higher value, and since it's an upper sum, I draw my box to the higher value. So my upper sum is going to be this width of 1 times the higher y value of the first window, width of 1 times the higher y value, width of 1 times the higher y value, and then width of 1 times the higher y value. So I end up getting, and again, you could factor out the 1 if you want this time, because if it's a constant width, it's kind of easier to do that. I end up getting 12 plus 11, right? So I end up getting that this is a 23. All right, so that's 3 area approximations using different y values for the curve. Now, I just want to show you one interesting thing. Let's say I had seen this not as, so let's say I'd given this to you as a table instead. So what if it was a table, right? And sometimes it's nice if they give you the data as a table, because if they'd given this to me as a table, my x-coordinates were -1, 0, 1, 2, and 3, right? And the y values were 3, 2, 3, 6, and 11. Well, I just want to show you that if we go back up for a sec, see if you can see the table and still see my LRAM. Yeah. So notice when we do LRAM, because it's the left endpoint, we used all of the endpoints except the 11, because you're using the left of the two endpoints, and every one of these endpoints, it will eventually be the left side of an interval. So I used so all but the rightmost y value, right? And when I did RRAM, you'll notice that I did all of the values except for this original 3, right? So when I do RRAM, I do all but the leftmost y, which is just kind of a shortcut if you wanted to look at it that way. All right, so moving on. You're going to go ahead and try a P1 the same way. You can pause me if you want to try this on your own. Again, if you like it better as a table, you can certainly do that, right? So I'm going to go from -1 to 2 in 3 boxes. So the first thing I need to do is figure out the width of my boxes. So 2 minus a -1 over 3 boxes is a 3 over 3, which is a 1. So my width is 1. And then, again, if you like it better as a table, you could certainly do that. But let's go ahead and walk through my LRAM. So it's going to be the width of 1 times, so in this first interval, right, I'm going to use the left y value, which is going to be a 2, right, plus the next interval, right? So the next interval, I'm going to use the left y value, which is going to be a 1, right? The next interval, so this is my interval, right? The trick is that in the next interval, I'm using my left y value, which is a 0, right, which does happen. So my left of the two y values, one was a 0, one was a -7. So I end up getting 2 plus 1 plus 0, so I get 3. Right? If I do LRAM, which I'll do in red again. So if I do LRAM, right, it's going to be that width of 1, and then in the first interval, right, this is my first interval, I'm going to use the right of the two y values, right, so height of 1, plus my second interval, I'm going to use the right of the two. Well, the right one is 0, so there's no height to that box, right? And then in my last interval, right, I'm going to use the right of the two intervals, which means I get a -7, right? So I'm going to get that this is approximately a 1 minus a 7, so I get a -6, right? And then for lower sum means you're just always taking the lower value, right? So lower sum means I'm going to take the lower of the two y values in every interval. So in the first interval, my choices are 2 or a y value of 1. Well, I'm going to take the 1. In my second interval, my choices are a 1 or a 0. I'm going to take the 0. And in my third interval, my choices are a 0 or a -7, and -7 is the more negative number, right? So I'm going to get that this is a 1 times a 1 plus a 1 times a 0 plus a 1 times a -7, which in this instance ends up being the right sum anyway. So it's the same as the LRAM, but that's the idea. All right. So what's a little bit trickier about this one is you're not given the graph. So using the method indicated, approximate the area of the given curve from 0 to 2 using 4 boxes. So the first thing you need to do is figure out the height of your boxes. So the first thing we're going to have to do is we're going to figure out that width is going to be b minus a over n, right, which in this case is a 1/2. So what that means, and I'm going to go ahead and make a table to do this because it's a lot easier if I have a table. So 0, 1/2, 1, 3/2, and 2, right? That's the endpoints I'm going to need. And then my y value is the square root of x. So the square root of 0 is 0, right? I'm going to leave this, it's up to you. You can leave this as a root 1/2 if you want. It doesn't have to be simplified. This can be a 1 or a root 1. It doesn't matter. Root 3/2 and a root 2, right? So not pretty. It is what it is, right? So LRAM means you're going to use all of the left endpoints and never the right endpoint. So my LRAM area, so if I want to do my LRAM, right, LRAM is going to be approximately, and so what I'm going to do is I'm going to do 1/2 times, and then since it's the same 1/2 for width, I can factor that out and just do the sum of all these. So 0 plus a root 1/2 plus a 1 plus a root 3/2, and that's it. Now, if you want to clean this up, you certainly can, but honestly, there's not much you can do to clean this up. You can make it slightly better. If you really wanted to, I guess you could leave this as a 1/2. You could make this a 1 over a root 2 plus, I guess you could call this a root 2 over 2, or root 2 if that makes you feel better. And this is a root 3 over 2. I don't really think this is making anything nicer, root 3 over root 2. So technically, I guess if you thought this made it better, but I really don't think it does, these all now have a common denominator. So you could make this a 1 plus a root 2 plus a root 3 all over 2 root 2. I don't think that's better. I would have stopped here. But that's the idea. Okay, so again, it's LRAM, so I'm never using the right endpoint. Now, MRAM's a little bit trickier because here's the problem with MRAM. MRAM means that I need the midpoint of each interval. Well, if these are 0 and 1/2, the midpoint, right, would be half of 1/2, which is a fourth. The midpoint here would be 3/4, right? The midpoint here would be 5/4, right? And the midpoint here would be 7/4, right? Because this is 6/4 and this is 8/4. So basically, I need a table that looks like this. What are the midpoint y values? Well, the midpoint y values, right? The midpoint y values are going to be the y values I get when I plug in the square root of these quantities. So square root of 1/4 is at least a little bit better. The square root of 1/4 is a half, right? This square root of 3/4 is a root 3 over 2. The square root of 5/4 is a root 5 over a regular old 2. And the square root of 7/4 is a root 7 on top of a 2. So it's not great, but my MRAM ends up being the width, which is the 1/2 times the sum of all these things. And that's really as nice as it's going to get if you want to put them all in one fraction because they all do have a common denominator of 2, right? You could make this 1 plus root 3 plus root 5 plus root 7 all over 2 times that common denominator, which would be 2 times 2, right? So if you wanted, I guess, the best version of this really ugly answer. Now, if this is a calculator section, obviously you could just type it in your calculator, but that's the idea. So MRAM's a little bit trickier. It is more accurate than the other approximations by a significant margin. All right, so you're going to give this one a try. So using the method indicated, find the area under the curve. You're going to do from -1 to 2 using 6 boxes. So first thing you have to worry about, right, is you need to find the width. So the width is b minus a over n, which in this case is 2 minus a -1 all over 6, so my width is 1/2. Right? What that means is I really need a table of these values, right? So when I go to do LRAM, I'm starting at -1, right? Then -1/2, and 0 because I'm going by halves, right? That's the width is by halves. 3 halves, and then finally 2, right? And that's the interval I was given. And then I want my y value, which is 2x squared plus 3. So not going to be the most fun thing in the world to find all of these, but you'll survive. So 2x squared is going to be a 2 times a 1 plus 3, so that's a 5, right? 2 times x squared, well, this one right here is going to be a 2 times a 1/4 plus a 3, right? So that's a 1/2 plus a 3, so you can make it a 3.5, you can make it a 7/2, I don't care. When you plug in 0, you're going to get a 3, right? When you plug in 1/2, you're going to get exactly the same answer you got when you plugged in -1/2 because you're squaring. When you plug in 1, you're going to get the same answer you got when you plugged in -1 because of the square. When you plug in 3 halves, you're going to get a 2 times 9/4 plus 3. Well, 9/4 times 2 should be 9 halves, so this is a 7.5, right? And when you plug in the 2, you're going to get a 2 times 4, which is 8, plus 3, which is 11. So you could leave it as decimals if you want. You could make them into fractions. I don't really care. So your RRAM, right, is going to be approximately the common width, right, times, and then you're going to take everybody except the 5 because it's RRAM. So you take everybody but the leftmost endpoint. So 3.5 plus 3 plus 3.5 plus 5 plus 7.5 plus 11, right? If I add the 3.5 and the 3.5, I'm going to get a 7 plus 3 is 10, right? We get a 15 with the 5. And then a 22.5, which means we should get 33.5. So we get that this is a 1/2 of a 33.5. You can either go ahead and cut that in half as a decimal, which is fine if you want. Let's see, that'd be 16.5 plus a 0.25. So if we do that way, we get 16.75. Should pan out. And if we want instead, we could have treated the 33 halves as a 67/2, right? And so we would also be able to say that this is a 67/4, which is 16.75, so yay. All right, so there's my RRAM. And again, you might have a calculator for some of these, but we're just kind of walking through what it would look like if you didn't. Now, MRAM's tricky. MRAM's definitely harder here because MRAM means you need the midpoint of all of these intervals. So you need the thing that comes between -1 and -0.5, which is -3/4, right? And this is -1/4, and this is regular 1/4. This is 3/4, and 5/4, and 7/4. So what you're going to have to do is for your MRAM, you're going to have to make a table that looks like this. -3/4, -1/4, 1/4, 3/4, 5/4, and 7/4. It's not super fun, I'm going to be honest. So the good news is that once you find a couple of them, you'll be able to reuse the answers on the other side. So because it's an even function, right? So this is going to be 2 times a 9/16 plus, well, that's not going to be fun at all, but I'm going to take this 3, and I'm going to pretend that this 3 is 24/8. The reason I'm going to do that is all of these are going to come out with 8s on the bottom, so if I call it 24/8, it's going to be easier. So this is 9/8 plus 24/8. So I'm going to get that this is 33/8, which also means that the other 3/4 is going to be a 33/8. The 1/4 is going to be a 2 times 1/16 plus 24/8, right? Well, that's 1/8 plus 24/8, so that's 25/8, and I can do the same thing here, right? The 5 is going to be a 25 over 16 times that 2 plus a 24 over 8. So that's a 49 over 8, right? And then the last one is going to be 49 over 16 times that 2 plus the 24 over 8. So it's going to be 49 plus 24, which should be 73. Right, so that's disgusting. Those are all my y values. So then here's the super fun part. My MRAM, right, is going to be my width, and then I'm going to add all those y values. So 33, here's the nice thing, at least. They're all over 8, so I'm just going to go ahead and know that they're all over 8 and get a common denominator. I don't expect that you're necessarily going to see one this tedious on an AP, but it's worth knowing that this is how you do them. All right, so when I add them, let's do the easy ones first. These guys give me a 50, right? So 50, these guys give me a 66. And you know what I'm going to do? I'm going to cheat. I'm going to borrow one from here. So that's a 50 and a 72, right, which should be a $1.22. So 8 and a 3, carry the 1, 238. So after all that work, boy, that's good times. I think I get 238 over a 16. And you can cancel a 2 out of that, right? So that'd be a 119 over an 8. And that's about as nice as it gets. Or you could get a decimal equivalent. So don't get me wrong. I get that those are tedious. I don't think that you're necessarily going to see one as tedious on an AP, but that's the gist of it. All right, so now let's go ahead and walk through what you're more likely to see on an AP. So sometimes you'll be given a table of values for a function that'll be all the work that you have to work with. When that happens, you don't get to choose boxes of equal width. The widths will be provided for you on the table. So example 3. A particle travels along the y-axis such that its position is given by y of t measured in meters, right? Some values of the velocity of the particle, v of t, are given below. Given that the initial position of the particle was y of 0 equals 5 meters, use a left Riemann sum, so see they're going to tell you how to do it, with 5 boxes to give y of 10. Well, we know y of 0 and we want y of 10. That means what we need to find is we need to do LRAM, right, for 0 to 10, right? So if we want to do that, here we don't get to choose the width of the boxes, right? Notice that if we're doing LRAM, we never use the rightmost endpoint. So the width of the first window is from 0 to 4. So this is going to be 4 because that's the width. And then I'm choosing the left endpoint, so 4 times 1, right? Plus the next box is from 4 to 7. That's a width of 3. And then I choose the left endpoint, which is 3, right? Because it's LRAM. The next box is 7 to 8. That's a width of 1. And then I choose the left endpoint, which is 2, right? And then the last box is a width of 2, because from 10 to, 8 to 10 is 2, right? Times I choose the left endpoint, right? So what's going to happen is that the area, the accumulation of change, is going to be 4 plus 9 plus 2 plus 10, right? Which seems to be approximately 25. So since that's the value, I know that y of 10 minus y of 0 is approximately 25. Well, I know y of 0 is 5. So y of 10 minus 5 is approximately 25. Add the 5 over, and I'm able to get that y of 10 is approximately 30 meters. So notice I had to use the approximately symbol because I didn't actually find the area under this curve. I found the approximate area under this curve. And notice that I had to use the windows I was given from 0 to 4. That's my width because I don't know what the curve looks like between 0 and 4. I can't make educated guesses. I don't know if it's a line, if it's a curve. I have no idea what's happening. So I can only use what's given to me. This is much more likely to be what you'll see on the AP rather than these problems that we just did that were really tedious gut busters, right? You're much more likely to see something like this. All right, so go ahead and give P3 a try. And I'll walk through it, so pause me if you want to stop me. A particle travels along the x-axis such that its velocity is given by v of t in meters per second, right? Some values of the acceleration of the particle, a of t, are given below. Given that the initial position, sorry, I meant initial velocity, ignore that, initial velocity of the particle was v of 0 equals 3 meters per second, use a right Riemann sum in 6 boxes to approximate v of 15. So again, here's what we know. We know v of 0, right? Which happened to be the same as the acceleration, but it's not because that's just a coincidence, right? and we want v at 15. So v of 15 minus v of 0 should be approximately my RRAM sum, right? So it should be approximately the RRAM that I get from 0 to 15. So my job is to find that RRAM value and then go ahead and solve for v of 15. So I know that I'm never going to use the left endpoint because it's RRAM, and then I have to pay attention to the different widths in the table because that's the trap, right? So my RRAM value is going to be a width of 3, right, because from 0 to 3 is 3 units wide, times the right y value, which will be the -1, plus a width of 6, because 3 to 9 is 6, times the right, and if you want, you can even cross off the values as you go, times the right y value, which is going to be the -2, right, plus a width of 1 times the right y value, which was the 5, right? And again, it's the right of the two y values in this interval, right? So this is one y, this is the other. I picked the right one. Not right as in correct, right as in left versus right. The next width from 10 to 12 is 2, right? And then I pick the right endpoint on that interval. Well, that's going to be the 4, right? And then for the last interval, the width is from 12 to 15, which is a width of 3. And then I pick the right y value, which is the 2, right? So that's my width and that's my height. So I can clean this up a little bit, right? This is a -3 minus a 12 plus a 5 plus an 8 plus a 6, right? So if I put my negatives together, this is a -15, and this seems to be a +19, so I should be getting a 6, right? So v of 15 minus v of 0 is approximately a 6 meters per second. But we know that v of 0 was 3, right? So v of 15 minus 3 meters per second is approximately 6 meters per second. So add that 3 meters per second over, and we get v of 15 is approximately 9 meters per second. Cool. All right, so that's the idea. Moving on. Okay, so how can you tell if LRAM or RRAM is an under or an overestimate? So in this case, LRAM and RRAM being an under or overestimate are all about whether the function is increasing or decreasing. So let's look at this window, right? So I'm going to be really lazy, and I'm just going to do it in 2 boxes, okay? I can't do it in 2 boxes. We'll do it in 3 boxes because that's the window I gave myself. So we'll do both of these in like a handful of boxes. So because this function is increasing, see how this function is increasing? The left value is always lower than the right value, so LRAM would be an underestimate, right? So if the function is increasing, the right value is always the maximum. So see that LRAM would be an underestimate because the left value is always the minimum on an interval if the function is increasing, and by the converse here, RRAM would always be an overestimate because the right value is always physically higher, right? If a function is decreasing, like this function here, well, now the y value is always the higher value. So look, the y value, right? Not y value, the left value, my bad. The left value is always the higher y value, right? So LRAM is an overestimate, but the right of the two values, because the function is decreasing, sorry, I meant to switch colors, the right of the two values is an underestimate, right? And you can also see this by physically drawing it on your paper, right? But the problem is that usually the AP is going to ask you to justify this, and if you're asked to justify why LRAM or RRAM is an over or underestimate, you're going to want to use talking about the functions increasing or decreasing, and that's really what it comes down to. All right, so there are 2 other common area approximation methods that do not use rectangles. The trapezoidal approximation, you'll sometimes hear that. You'll sometimes hear that called the trapezoid rule, right? So trapezoidal approximation or trapezoid rule, okay, which is very likely to be on your AP in some fashion, and Simpsons rule, which I've never seen on an AP, but I will show you at the end of this video anyway, just for your own benefit, just because it doesn't hurt to know it. It won't show up on your AP, but it doesn't hurt to have seen it once. So trapezoidal approximation. Recall that a trapezoid has 2 parallel sides that we call bases, so like B1 and B2 here, and 2 other non-parallel sides. The height of a trapezoid is perpendicular to the bases, right? So the area of a trapezoid is given by, and yes, you should totally memorize this, 1/2 the height times the sum of the bases, or area equals 1/2 h, and then in parentheses B1 plus B2, or B sub 1 plus B sub 2, depending on how you choose to say that. But you want to memorize this formula. So a trapezoidal approximation is just the sum of several trapezoids. That's it. So if you know the area of a trapezoid, then you can figure this out. So the bases are the y values, because what's going to happen is on your graph, right, the bases are going to be these parallel lines, and then the trapezoid is drawn by connecting these two sides, right? So they connect the y values. So your bases are the two y values on the sides of the interval, and the height that we're talking about is that b minus a over n. It's that width along the x-axis. So let's go ahead and walk through this. So here's an example, like this is a visual of a trapezoidal approximation. If you were going to approximate this curve in 3 trapezoids, right, you can see here, right, that my width, which is the width along the x-axis, that delta x is actually the height for a trapezoid, right? This is my h, right? So in this situation, my h is 4 minus the negative 2 in 3 boxes. That's 6 over 3, which is why you can see that each of these has a height of 2, right? So all of these, my height is 2. And then the y values, right? These y values are the bases of the trapezoid. This is a 3 and a 2. This is a 2 and a 3. This is a 3 and a 6, right? So let's call this trapezoid A, B, and C. If I wanted to approximate this area, the area of trapezoid A is 1/2 the height times the sum of the two y value bases, right? B would be 1/2 times the height times the sum of the two bases. And C would be 1/2 the height times the sum of those two y value bases. So you could find each one of these individually. If you did, you'd get a 5 and a 5 and a 9. And so you'd get that the trapezoidal approximation is approximately a 19. The other way to do this, and this is kind of a cool trick, is if you notice when the height is constant, so in this case, see how this is constant, you actually could factor out, so if the height is constant, right, if constant, right, if the height is the same for all these values, you could actually factor out that 1/2 the height, and what happens is this base only got used once, but this base got used twice because it was base 1 for one of the trapezoids and base 2 for the other, so 2 times this base, plus this base got used twice, right? And then this base only got used once. And we're going to learn a trick to figure that out in a minute. It's a trick that only works if the bases are the same, right? Or rather, if the heights are the same. So let's go ahead and walk through. So on the table below, we're given some values of f. We're going to use this information and 4 trapezoids to approximate the area under the curve from 0 to 8. So notice that they're not 4 trapezoids of equal height, right? So the height here is a height of 2 from 0 to 2. This height will be a height of 3. This height from 5 to 6 is a height of 1, and this height will be a height of 2, right? So my first trapezoid, right, is going to be 1/2 the height, which was that 2, times the sum of the bases. My second trapezoid, right, from 2 to 5 is going to be 1/2 the height times the sum of the bases. My third trapezoid, which would be from, so if it helps, this is the one I called A, this is the one I'm calling B, the one from 5 to 6 would be C, and the one from 6 to 8 would be D, right? So 1/2 the height times the sum of the bases, right? And the last one would be 1/2 the height from 6 to 8 is a 2 times the sum of the bases, right? So this is going to be a 1/2 of 2 I could just get rid of, and that's fine, although I'm going to argue that some of these don't work out that well, so you might as well keep the half. So this is going to end up being essentially 2 halves, right, times a 13. So I'm going to go ahead and make this a 26 halves. I know it's just a 13, but I promise there's a logic for keeping the half. This is 3 halves times 5, so that's a 15 halves, right? So see how that's also over 2. This is 9 halves, right, because it's 1/2 times 9. And this one's going to end up being the 2 times the 8, so that's 16, so 16 halves. It's up to you. I think it's a little bit easier to keep them all together. I really don't care. It's entirely what you want. So what that means is that my approximate sum is going to be 26 plus 15 plus 9 plus 16. Well, 9 and 16 is a 25, right? If I add the 15 to that, that's a 40. So I end up getting 66 over 2, which is 33. Right, so I get approximately 33. There were no units given, so I don't need any other units included. All right. P4, go ahead and give it a try. It's the same concept, right? So you're going to use 5 trapezoids, right? So one from here to here, 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 and one from here to here, right? Notice that the heights vary, right? The height from 1 to 2 is just a difference of 1, but the height from 2 to 6 is a 4, right? So I'm going to go ahead and call this A, B, C, and D and E because I think it's easier to label them, right? So I'm going to get 1/2 the height times the sum of the bases. For the second one, 1/2, the height from 2 to 6 is a 4, times the sum of the bases. For the next one, I'm going to get 1/2, the height from 6 to 8 is a 2, so 2 times the sum of the bases. That was an 8, by the way, it doesn't look super like an 8. My next one is 1/2, 8 to 11 is a height of 3, and then the sum of the bases would be 1 plus 2. And then for my last trapezoid, 1/2 the height, which is from 11 to 12, so that's 1, times the sum of the bases. Okay, so when I find all these values, I'm just going to find them individually. You could write it all as a chain. I just think it's easier to split it into 5. This ends up being 8 halves, right? You can either leave it as 8 halves, or you can make it 4. I'm going to argue that some of these won't cancel, so it might be easier to leave it as 8 halves. This one, right? Now this one is going to be a 4 times an 11 all over 2, so that's 44 over 2, right? This is going to be a 9 times 2, so that's 18 over 2. This is going to be a 3 times 3, so there's that 9 halves. That's the first one that didn't cancel, even if I wanted it to. And then the last one is going to be an 11 halves. Now, interesting side note, these two, you could just cheat and say, oh, together these two are 20 over 2, so they're 10. And then it's not so bad to simplify the rest of them, right? Because then you can just not worry about fractions anymore. So your answer is going to be the sum of these 4 numbers, right? So your trapezoidal approximation is going to be 19 plus 26, right? So it should be 45. All right. So how can we tell if a trapezoidal approximation is over or under? Well, that one's about concavity. So if your curve f of x is concave up, so here's an example of a graph where it's concave, where f of x is concave up, you can see that the trapezoids cut above the curve. See that yellow area? That yellow area is too much, right? Too much. But if f of x is concave down, you see how the trapezoids are under the curve, so they're cutting not enough, so there's not enough. So if you're asked if a trapezoidal approximation is an under or overestimate, what you're really being asked is what is the concavity of the curve. So just a reminder, LRAM and RRAM, if you're asked if it's an under or over approximation, the answer will have to do with whether the function is increasing or decreasing. If something is trapezoidal and you're asked if the function is an over or underestimate, or if the value is over or under, you can tell by the concavity of the function. So the last thing we're going to mention, and I'm not going to spend any real time on it, just want to throw it out there, there is one more accurate way to approximate things. So, and to do that, we should, I'm sorry, it's not the last thing. We're gonna mention, I apologize, we're gonna go over the trapezoidal rule, that shortcut that I talked about a little bit. So, for the trapezoidal rule, and I mentioned this briefly before, you don't have to do this. It's absolutely fine if you don't do this. You can just add up the individual trapezoids. But if you have trapezoids of the same height at all times, that b minus a over n, then you can cheat and factor that out in front. And what's going to happen is you're going to use all of these endpoints twice, right? You're going to use them all twice because each one is both base 1 and base 2, except for the first and last endpoint. So what's kind of cool about that, right, is it's a lot faster to do it this way if everything's the same height. So let's walk through 1 or 2 like that, and then we'll talk about Simpsons, which is what I thought this next slide was. So using 6 trapezoids of equal height, approximate the area under the curve f of x equals x squared from -1 to 2. Okay, so since it says of equal height, the height is b minus a over n, right? So that's going to be 3 over 6, or 1/2. What that means is that I'm going from -1 to -1/2 to 0 to 1/2. What am I going to 2, right? To 1 to 3 halves to 2. Good times. All right. So that's my x value, right? And then my y value is x squared. So this is going to be 1 and 1/4 and 0 and 1/4 and 1 and 9/4 and 4. Okay. So basically what's going to happen is all of these get used twice, but the ones on the ends only get used once. So my trapezoidal approximation is going to be 1/2 that height, right? Because this is the 1/2 and this is the height. And then I'm only going to use the first base once, but I'm going to use 2 of the second base and 2 of the third base and 2 of the fourth base, right? And 2 of the fifth base and 2 of the sixth base. I'm out of room. And I'm only going to use the last base once, right? So I get that this is approximately, I'm going to make that a 1/4 in the front, right? This is a 1 plus a half plus a 0 plus another half plus a 2 plus 9/2 plus a 4. So I get that this is 1/4. I'm going to go ahead and cheat and add the stuff that's not halves first. So, excuse me, so I get a 1, a 2, and a 4, so I'm going to get a 7. Plus, this seems to be 11/2. Unfortunately, that doesn't go away. It's still a half, so I get 1/4. This will be 14/2 plus 11/2. So I'm pretty sure I get 25/8 because it would be the 2 and the 4 on the bottom. So that's a lot easier than making 6 ugly trapezoids and having to add them. But again, it's a cheat that only works if you're using equal heights. All right, so let's go ahead and try one more, and then we'll talk about Simpsons. So using 4 trapezoids of equal height, so that means you can use this shortcut, approximate the area under the curve f of x equals x cubed on the interval from 0 to 1. So my height is going to be 1 minus 0 over the 4 boxes you're using, so the height's 1/4. That means that the table you're going to need starts at 0, 1/4. You can make it 2/4, right, if you want, or you can make it a half. It doesn't matter to me. I'm going to argue that there probably is a strong case for making it 2/4, but we'll deal with that later. So, and then x cubed is going to be my y value. So 0 cubed is 0, 1/4 cubed is 1/64, right? 1/2 squared is 1/8, but it is worth noting that that's the same as 8/64, right? 3/4 cubed is going to be 27/64, right? And 1 cubed is going to be 1. So my trapezoidal approximation is going to be 1/2 the height, which here was a 4th, right? And then for the bases, these all get used twice. The ones on the end only get used once. So 0 plus 2 times the 1/64 plus 2 times, and again, you can leave it as a 1/8 if you want. There is an argument for making it an 8/64. And I only use the endpoint one once. So the 2/64, so out here I get a 1/8, right? On the inside I get a 0 plus 2/64 is a 1/32. You could go ahead and make this a 1/4, but again, here's my argument. You're going to need to combine them as like terms anyway, so it's probably easier to just make this 8/64 times 2, which would be the same as 8/32. And I realize you're probably saying, but 8/32 isn't simplified. It's true, but it's getting me to my common denominator faster. And to the same effect, I'm going to turn the 1 into a 32/32. So I get that my trapezoidal approximation is approximately a 1/8 times everybody's over a 32 now. So 32 and 8 is the easiest to add first. I'm going to start with that. That's a 40, and this is a 28. So I get 68/32. I can cancel 4 out of that, right? So that's a 1/8 times, if I cancel a 4, this is 17/8. So I'm going to get that this is 17/64. That's my trapezoidal approximation. All right, so very last thing. You're not going to have to do Simpsons rule on your AP, but I just want to throw this out there. So trapezoidal, of all the approximations we've discussed today, trapezoidal was the most accurate. It's also, in some ways, the most tedious, but it is the most accurate. The second most accurate is LRAM, which you probably recall from the beginning of this video was also tedious. Simpsons is actually more accurate than either of them. Essentially, Simpsons uses quadratic regressions to, instead of making a straight line between these two, see how that would be a straight line, right? That's trapezoidal. Essentially, what it does is it does a quadratic regression with 3 points to make a quadratic, right? And that means that the concavity is not as big of an issue as it was with trapezoidal approximation. So really, for me, the way I memorize Simpsons rule doesn't have a geometric counterpart. You have to memorize the formula. So I look at the trapezoidal rule and I look at what's different. The trapezoidal rule has a 2n here because it's 1/2 the height, right? And so that's a b minus a over that 2n, right? That's why that's a 2n. The Simpsons approximation has a 3n, right? By the same token, we saw that in the trapezoidal approximation, all of these internal coefficients were 2's. In the Simpsons approximation, they alternate 4, 2, 4, 2, dot, 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 until they end in a 4. They both start and end in a 4. Notice that the first terms still have no coefficient. The coefficient is just 1, rather, right? So you don't have to know Simpsons rule, but I just want to show you that the easiest way to learn and memorize Simpsons rule is actually to do it in a way that essentially analyzes how it's different from the trapezoidal rule. But you're not going to have to do it. I just want to throw it out there so you'd seen it. So that's the end of our Unit 6, Section 2.